Uh, Hello everyone. Welcome to the session of book club for designing data intensive applications. In today's session, we are going to discuss about Zookeeper. So last time we discussed how we can use Zookeeper for leader election. This time we will see that. This time we will see that in action uh, I- by actually running Zookeeper and having a server and various clients which can choose a leader among those clients. So we will do that demo, and I think that's the last part of this consistency and consensus chapter. After that, uh, we can probably revise the chapters that we have discussed before. So I don't know if you all have noticed the maps, like each of the chapters, they have a map at the beginning of the chapter. And these maps, each of the map has kind of a nice like summary of each of the chapters. So probably we can pick a few of the maps and see and discuss what we have learned so that we can recall what we have all discussed, right? So yeah, so that is what I was thinking of doing today. Okay, so let's start with the Zookeeper part. Last time, as we discussed, that we can use Zookeeper for leader election, right? So basically, uh, let me quickly draw that diagram again, and then we will implement that design. So basically, we will have a Zookeeper client, right? Sorry, we will have a Zookeeper server. So the server will be the one which will be hosting Zookeeper, and this was also last time we discussed that this server, there could be multiple nodes in this server, and this constitutes an ensemble, right? So in our demo, we will create only one node for the server, but it is highly recommended to create multiple nodes for replication and fault tolerance, right? But for simplicity, we will create just one node. And then on the other hand, we will have some clients. So these clients, they will connect to this server, and we will choose a leader among these clients, right? So we have to choose a leader. So they will use Zookeeper, this service, to decide a leader among them, right? Okay, so basically, so first start the server, and then so basically I downloaded Zookeeper from the Apache site, and I got this Zookeeper folder. So here, this bin has these scripts to run server and to run client, right? So to run server, I will just say bin zk server zk server. Okay, so yes, this is our server which is running. So now we have this server running, and it's running on port 2181. So in the config file, we have set up the port, right? So this is the port where this server would be running. So now the clients who wants to connect, they have to use this port. So when I will, so in another command prompt shell, uh, create, I will create a client who will connect to the server. And the command was ZK client. Okay, server. This is the server. Yeah. So ZK client then connect to the server 127.0.1. Okay, so yeah, so this is the one server which has been connected. This is one of the clients which has been connected to the server. Uh, so basically now it has access to all the files, the file structure which the Zookeeper supports. So in the help command, these are the set of commands, right? So add, watch, close, config. Uh, okay, so ls root, right, will show me all the nodes that I have at the root level, right? So basically, I created these nodes before leader election, leader test, zookeeper. So these are those nodes. Okay, so now let's quickly create two more clients who will connect to this zookeeper, and then we will do our stuff. So ZK client minus server 127. So this is our second client. This is our third line, right? So now the problem was that in these three, so like imagine these three clients, they are running on different machines, right? And we have to choose a leader in one of them, right? And we will take help of Zookeeper server. And then later we will see that if one of the client dies, right, and let's say it's leader, how the other client could be picked up as the leader, right? So to remind everyone, so uh, the way we discussed how we would do that is that we will create a main node in the Zookeeper. Let's call it leader election, right? So and then all of the clients, all of the candidates who wants to be the master, they will create ephemeral sequential nodes, right? So ephemeral is session ephemeral, which means if the session is closed. So each of these clients, it has created this a session with the server. So as so these nodes which we create as ephemeral nodes, as long as the session lives, these nodes lives, and as soon as the session is dead, these nodes die, right? And sequential means that they should be created in an increasing sequential order. So we will create, each of the client will create this ephemeral sequential children, right? And then also the each of the children will add a watch on the node uh, whose this sequential ID is just less than this node, right? So 2 will add watch on 1, 3 will add watch on 2, and like this, right? And then so now the node which has the least ID, that is the leader. So 1 will be the leader. And for the failure detection, as soon as the 1 dies, 2 will be get notified because 2 has added watch on 1. So then 2 will come to know that 1 has failed. So now 2 has to check whether now it is in the front of the line, whether it has the least ID, and then 2 could be the master, right? So the same thing we are going to do here. So basically we have these 3 nodes. So any one of them can first create that main, right? So to create a node, the command was connect delete history. Create, okay, the command was create, right? So this one, create. So create, then minus S is to create a session FM. No, I think minus S. So we need to specify two parameter, minus S and minus E. So minus S is to create sequential and minus E is to create ephemeral node. But okay, but this is the main node, right? This is this main node. So this does not need to be ephemeral and sequential. So this is just a node. So we will create this one node. We will name it leader election demo, right? So now if I will do ls, so now we have this node, right? Leader election demo. So this is the main node, and the client will create, now the client will create a session ephemeral node inside it. So create minus s minus e, and so we have to create it inside leader election demo. And so this is candidate 1, right? Okay, so it has created this node, right? And it has given this name. So similarly, this other client, so we have these bunch of clients, right? So this client will also create another node. So this will be our first client. So this will create a node, create minus S minus E, leader election demo. This is our candidate 2, right? So this will create this candidate 2 node, right? And then this is third, so this will create a third node. Create minus S minus E, leader election demo, candidate 3. Right, so we have
So,
created 3 nodes.
Abhishek, quick question here that though I
Just,
missed that how these
just
node actually know that whether I have to create a node 1, 2, or 3.
oh, sorry if someone was speaking. I had my headphones on, but can you repeat again?
Yeah, so Abhishek, my question is that how these client node know that, I mean, what counter they have to use 1, 2, 3 in terms of.
Uh, no, they can use any counter, like, so they will get an increasing. So actually, okay, I should have given some ID, but see, like, uh, So Zookeeper will automatically assign them an increasing ID. They don't need to
Okay,
know.
so they just pass the ID and Zookeeper append that incremental ID to that, right?
Yeah, yeah.
Okay,
I think
got it.
Abhishek,
Yeah.
it would have been better instead of you giving the prefix as candidate 1, 2, 3. Even if you
Mm-hmm.
have kept the prefix as just candidate, it would have it would have created as number 1, 2, 3.
Okay.
Right.
Okay. Yeah, let's do that. Okay, so let's do that. Uh, so I will create another node, create uh, leader election ST skills, right? So this is my main node, and then create -s -e. So leader election ST skills. So let's each one of them, let's say I am A, right? So this is A, and so I'm not giving any sequence. I'm just to differentiate that there were three clients. So this is candidate A, B, C, right? I'll give these names. So candidate A, this is candidate B. So this is,
path, the name should be same. You can give it candidate itself. Then it will automatically increment it.
no, it's why the name should be same, like how, like each one of them is,
No, no, no. Actually, you try to create that particular Z node
Hmm,
and you say that sequential and ephemeral, so that it Zookeeper automatically figure out whether it is the first one or not. So the path, it is the common path that actually tells us whether both the clients are uh, trying to create the same Z node or not. If you're doing candidate A and candidate B, it may think it as different ones.
Yeah.
okay,
These will be two different nodes now.
okay,
Yeah. So the last zeros are there, right? So
Mhm.
that is the appended one. So
Okay,
if you have created a candidate itself, candidate something like that, it will be there.
okay. So yeah, it is automatically giving them a unique ID. So okay, we don't.
Yeah, do a candidate A. Now it will increase to one.
Yeah. Or you can use the candidate A from all the clients.
Let's do this. So this is candidate one, right? This is one of them. Then delete leader. Okay, now I will create another one, right? And here I will create another one. So yeah, so first I created here. So the ID was 002, right? Then this one had 3 and this one had 4, right? So now the next step is that uh, we need to add watch, right? So basically, each one of them will look at the children of the master and see who is the one whose ID is just lesser, and then it will add a watch, right? So let's say, so in each one of them I will write this code, right? So basically you will be writing this code, but here we will do it manually. So we will investigate this main parent node, right? And see that it has these three children, right? 002, 003, 004. And my ID is 002. So, and I will see, is there someone whose ID is lesser than me? There is no one. So then I will not add watch on anyone, right? Similarly, I will do it here. ls leader election st skills, right? And here I will see that again there are three and my ID was 003. So I have someone whose ID is just lesser than me is 002. So I will add a watch on that. So to add a watch, the command was using get, right? Get minus s minus w and whatever node we want to add watch. Get minus s minus w. And I want to add watch on this client, right? So leader election st skills. Yep. So we have run this command and okay, and now yeah, it has added watch onto. So similarly, we will add watch. So here the again leader election st skills, and I will add watch on 003. So get minus s minus w leader election st skills. Okay, so now we have set this up, right? We have added watch. Each one of them have added watch. And so now, again, in the code, we would have written the code like this, that initially during this setup, that investigate the parent node. If your ID is least, right, then you are the leader. If your ID is not the least, then look at the one whose ID is lesser and add a watch. So when the code would have executed on this node, it would have seen that its ID is least, right? And so now this is the leader. When the code executed on this node, the same code, it will see that its ID, there is a node with one ID lesser. So it will add watch on this. And similarly, this will add watch on 003, right? And this is our leader. So now basically what we have to do is we have to fail the leader, right? So we will close this one. So this was the leader. So we will basically close this session, right? And here, so we saw that the session was closed, right? And so basically now, after a timeout, this node should receive a watch event. This client should receive a watch event. So let's see. Yeah, see, so this has received a watch event, right? And again, in the watch event, you will write the same code that if now your ID is least, you are the leader, else else update your watch, right? So this has received the watch event. So now basically this node would have identified itself as the leader, right? And you can also see that in the watch event, you saw that the watch event say that this node was deleted 002, right? So now this node was leader, and let's say now this node, this second node also dies. So again, this session was closed. So after a timeout, this node should receive the event.
It 30 seconds timeout, right?
Yeah, 30 seconds. Yeah. Okay. So here is the. So I think the timer is set here, this tick time, and I think it's 20 seconds. So after 20 seconds, so in the configuration, we can set up the time. This is 20 seconds. So, right. So, yeah, I think that was how I wanted to show how we can use Zookeeper. Are there any questions?
So the zookeeper have to maintain the total order itself, right? Because like each client register, you know, there could be both client register at the same time, and then you know one client receive the list, say, you know, who's the leader, and the other client might receive a different list, you know, who's the leader or who before that. But yeah, so I think that they have to maintain the total order.
So yeah, when the node is created, Zookeeper ensures that each of the node will get an increasing ID, right? So now, now once we have ensured that, then like, so because this, basically, if you have created a candidate one, like if you have created this first node, right? And if you have created the second node, so like when you have created the first node, everyone will see the first node. When someone was creating the second node, even if the second node is not seen by other people, everyone still see at least that first node. So they know who is the least among them, right? And they know, so they can decide who the leader is. Basically, the nodes which come after might not be visible to everyone because that node was just being created. But to decide the leader, we are picking the least node, the one which has least ID, right?
Right.
Which will be seen by everyone. So.
But the watch list have to not depend on the leader, but depend on who previous client, yeah. Right? So suppose that, you know, I'm at the watch list to the previous client, and you know the previous client at that time like get deleted.
Yeah.
And what happened?
So so let's say we had this scenario, right? And one was the leader, right? So now let's say the leader does not die, but two dies, right? So when two will die, then three will get notification that two has died, right? So on the notification, we are writing this code that check that now if your ID is less, if your ID is less least, then you are the leader. Else, add a watch on the ID whose ID is lesser than you. So when the two dies, this will get the notification and it will execute the code. So it will look at the children of leader election. It will see, is the ID of three least? No, the ID of three is not least because one still exists, right? And then the second part is add a watch on the one whose ID is just lesser than me. So now three will add a watch on one.
I mean, like, you know, when I create client 3, right? And after I create client 3, I look at it and list client 2 was my previous node. I haven't added a watch yet, right? And now, you know, the first time I add a watch, I add the watch to client 2. But at that time, you know, it happened on the server, the client 2 get deleted. Then do I receive the, you know, what I'm going to do? Do I receive the error command?
Yeah, okay. So when you were adding the watch, you saw that client 2 was the least. And when you were adding the watch, at that time client 2 does not exist. So yeah, I think that then basically you will get an exception or something, and then you would have to do a retry and then again execute this logic. And then because basically then it is equivalent to setting a watch on the node that does not exist, right? So whatever the behavior is on adding a watch on the node that does not exist, I think it will throw exception or something. So then you will get the exception and then you would retry. So then when you will retry, you will see that, oh, the node is now 1. So then you will add a watch on 1.
So whenever you create a watch, I mean, if any update happens, either it can be update or even delete. So the one which have created that watch will get a notification. So I mean, and these notifications are also a one-time register thing. So you have to re-register again as well. So whenever you get a notification again, you actually need to check this whole sequence. I mean, you need to get what are the children of this leader election again, and you need to go through the list. And I mean, so basically it's a recursive kind of thing. So you need to check whether you are the least or not. If you are not the least, what is the node that is before me? So as you said, uh, 2 might have got disconnected and that node might not be there. So you will create a watch event on L1.
Yeah.
Okay. Yeah.
Okay, so yeah. Uh, so do we want to do a distributed lock as well? How we can implement distributed lock using Zookeeper? Or should we like move on?
Yeah, sure. We can, yeah, I think do distributed log.
Okay, so let's do a distributed lock scenario as well. So does anyone want to go over, like Leon, do you remember what was the algorithm of using Zookeeper to create distributed lock?
I don't remember.
Okay, so basically it's very similar. It's same as this, right? So basically, um, you will create nodes, right? And the one whose ID is the least, that node will have the lock, right? So in this case, one will have the lock, and then 2, 3, 4 have added watch. So generally in leader election, when leader dies, then the failover happens, right? But here it is a lock scenario. So basically, when you are done with the critical resource, you want to release the lock, right? So to release the lock, one will delete the node, right? Its node, because it is now done with that part. So it will delete its node. So as it will delete its node, 2 will get notified. And then 2 will now know that the resource is free and 2 has the least ID now. So now 2 can claim that resource, right? So this way we can implement distributed lock. So the one who has the least ID, they will get the exclusive lock. When they are done with their part, they will delete their node so that the other one can now use the resource, right? So basically, so let's create these 3 clients. So this is my client 1. So each one of them. So ZK client minus server 27.0.0.1. So each one of them will now connect to Zookeeper's session. So now we will create a parent node, right? So we have the this Zookeeper client 126.
I think the server died.
I'm sorry, what? No, server is running.
Oh, it's running.
Zookeeper client server 127.0.0.12181.
There is a typo in server.
Oh, yeah. Thank you. Okay, great. So we have this one, we have this one, we have this one. So, okay, so we have the list. So let's create a node. So this is the main node. So let's name it critical resource, right? And now I will create a ephemeral node inside it, minus S minus E critical resource. And again, this is one of the consumer. This is another one, session ephemeral node. Resource consume. This is the third. Okay, so we have these three nodes. So again, so each one of them, they will create a node and they will add a watch, right? So when this node was created, there was no one who had whose ID is less, and this one would have got the node. When this node was created, there was one of the client whose ID was lesser, so it will add a watch on that, right? So it will add a watch on critical resource consumer zero zero zero, right? And similarly, this one will add a watch on critical resource yeah, this will add. Again, right? So okay, so now they have added the watch. So now, so this node had the log. So when I'm done, right, I will with the critical resource, then I will release the log by deleting my node. So I will delete my node, delete. So I will delete, and now this will get a notification. So in the notification code, it will check whether my ID was leased. So it will see that this ID is leased, and then basically it can get hold of the resource now, right?
Mhm.
Okay, so this was how we can use it for distributed clocks.
There is sort of like right now the way it is like a queue, right? First come, first serve, but it's
Yeah.
an option like create a priority. So in case of the leader election, or even the clock, some client may have priority higher than the other, then they should be get the clock first.
So, okay, so setting up a priority, and what would be the scenario? Why would...
Yeah, so for example, we have multiple reader and one writer. So in some case we want all the reader priority for all the reader read the data first, and then the writer will be the last one. Like multiple reader and writer priority. But yeah, I just ask, maybe there's a feature in there, but that we can look at it later.
Okay, I don't know if so. Does anyone have the answer to this? I don't have the answer. Okay. Cool. Okay, I think that was pretty much it in this chapter. So basically, Zookeeper could be used to allocate work to nodes, right? And Zookeeper could be used for service discovery. So now, if you want to use Zookeeper for service discovery, it's very easy. So whenever you start up a new service, so let's say you had a service to provide you search, right? So whenever a new node comes up that uh, that is providing this service, search service, then it will create a session ephemeral node of the node ID, right? That this is my node ID and I am one of the node. If another node comes up, if you set up another node, then this will also create a node. So now basically, looking at Zookeeper, this parent node, you know that which of the nodes are active in the system, right? Because if any of the node dies, this node will automatically be deleted. So that's why you can use Zookeeper for membership services and service discovery, basically to know what are the nodes who are providing this service and which of the nodes are active right now, right? So yeah. So I think I had this for this topic. If there is nothing else, then we can move to the second part. Basically, we can, so I think we have discussed 7 chapters up till now, right? So we can do a brief overview of what we have discussed so far before moving on to the next section of the book. Okay, so let me open up this map. So yes, so what chapter should we start with? We have 40 minutes, right? So okay, let's go one chapter. So okay, let's first look at this chapter. So this chapter was consistency and consensus, right? So basically, we discussed what are the things we discussed in this chapter. we started with linearizability, right? Uh, so the linearizability was that you have multiple nodes in the system, and the linearizable system is the one which behaves like a single system as a whole, right? So each of the replicas, they are in sync and they act as one single system, instead of a non-linearizable system would be when the nodes, there is a delay in replicating the data, right? And if you get your data, then your system has different views of the data, right? So that is a non-linearizable system. And so few things we discussed, there were compare and set and increment and get operations, right? Then the other topic we discussed was what was this global constraints? I think they mean by global constraints, okay, are these global services that you can use to impose constraints on your system. So basically, if you have a bunch of services running and you want to implement a constraint that only one of them is a leader, then you can use these services to impose those global constraints, right? And basically, they can give you uniqueness guarantees, or they can provide you locks and all those things, right? This part of the book, somewhere we discussed about distributed transactions, right? That basically, if you have multiple nodes in a system which have your database, and you want to implement a transaction that span across multiple nodes, and basically, so now the problem is, the with transaction we want to follow acid properties, that it should be atomically implemented on both of the nodes, and or it should not happen on any one of them, right? There should not be anything in between, anything in or partial. So that actually becomes much harder to do when your data, when your transaction involves nodes on different machines, right? And so to do that, we discussed few algorithm. The main one we discussed was this two-phase commit, right? And then the other part which we discussed was total order broadcast, right? Basically, in which we were saying that that the messages, they have a strong ordering among them, they have a total order among them instead of a causal order, and basically the messages are replicated and broadcasted to other nodes in that same order, right? So this is used for state or machine replication, right? And then a lesser stricter order of total order broadcast was the causal order ordering, right? Where which just stores that what event happened after the another, right? So we discussed that total order broadcast is expensive, and in many situations you can use causal ordering, which is less expensive to do, and basically your application might not need a total order broadcast, it might just need a causal ordering, right? Then we discussed about Lamport timestamps, right? That we can use like how to use timestamps for ordering. So basically, if you use the day of the clock of your machine, then your ordering might be incorrect, right? So that's why you use, one of the things you could use is you could use Lamport timestamps for ordering, right? And so like I really, so see the, so this the main, this is the main mountain, which is Mount Consensus, and these are the like kind of the ashes out of it, right? So we use bunch of the things we discussed here to actually implement consensus, right? So basically in consensus, we use total order broadcast, like we discussed in Raft, right? That the Raft will replicate those messages across its node in total order broadcast. And the way it replicates those message, it is very similar to how two-phase commit operates, right? That first it will ask those nodes whether they can commit or not. When they reply yes, then it will say yes to the client, and then in the second part it will send a commit message to those nodes, right? And basically we build linearizable systems. We can build linearizable systems through consensus, right? That your system as whole will be linearizable, that it will have one view of the data, right? And then we saw that how this consensus could be used to put global constraints on your system if your application needs. So like if your application need to provide uniqueness guarantees, or if the application needs a distributed locking, then it can use these consensus algorithms to do so, and it can outsource that part to other services like Zookeeper and all. Right? Yeah, so that was my take on this chapter. Next, should we go look at chapter 8? Chapter 8, chapter. So this was chapter 9, right? Where is chapter 8? Okay. Trouble with distributed systems. Does anyone else want to like look at the diagram and go over, and then we can as a group overall discuss what were the things? Is it like, should we do this, or yeah, or if it's not so interesting, we can probably I don't know, we can, I don't have next chapter, but yeah, I was thinking to recall these chapters.
Yeah, I think this is good. We can, help us to review.
Yeah.
Going backward, I can talk quickly about distributed system. I don't remember a lot, but I can. So with distributed system, we have multiple nodes, right? And then because we have multiple computer, and each computer use the wall clock or network clock. But even with that clock, there's a time inconsistent between two computers, because one computer can run faster, the other computer runs slow.
Yeah.
And yeah, and the other problem is the process pause. We talk about like in Java, we say, okay, we want this one to run in let's say 4 seconds, but let's say we execute in 2 seconds, and there's a garbage collection. It pause the process right now, and they they halt all the thread, and then it do some garbage collection. By the time it's done, then we continue with the last 2 seconds, but at that time it's the 4 second allow already expire.
Yep.
So that's another problem. The other one, like the unbounded network delay. So network is unreliable. We don't know, when we get the let's say, even if we have one client and one server, and the client, send a request to the server. So one request can go to one route, the other request can go different route, depend on the network at that moment.
Mm-hmm.
Yeah. So yeah, that's it.
Yep. Thank you so much for the summarization. Yep. That's pretty much about this chapter. And if you look at this diagram, so you see that your distributed system, it has been like this octopus kind of structure, which has these problems. It is like it has holded your system, and it is making your ship to move. It is making harder for you to move your ship forward, right? Because of these problems that you have to deal with while moving in the sea with these kind of problems. So yeah. So this was this chapter 8, then chapter 7. Okay, chapter 7, transactions. Who wants to go over this one? Let's see who all we have. Okay, so we have Leon, Alex. Alex, do you want to try this one? Okay. Anyone else? I think who Uday, I think you often join these sessions, right? So probably you want to go over.
Transactions.
Yep. I mean, we can. So,
Sure. I mean, I may not be able to summarize in a good way like you do.
no, I mean, yeah, we will all go into it together.
Sure. So the applications actually try to do operations on the database. And when we, like increment, like a get or a set, something like these operations, they try to do on the database, and they need, uh, so if there are interleavings, the operations can have ambiguous behavior, ambiguous results. So that is the reason we actually, the applications need a transaction kind of concept, saying that uh, the reliable way, such that this transaction, the given operations execute in a isolated fashion, that they should execute in a parallel way, but still under the assumption that no other transactions can affect this behavior. So the database offers the different isolation levels. The strongest one is the serializable, and the other one is snapshot, MVCC, right? Snapshot isolation.
yeah, right.
And the other is couldn't remember.
Yeah, this one, read.
Read committed.
Read commit. They should. I thought there was something before actually. Sure.
Yeah, before was read uncommitted. I think the lowest is read uncommitted, right? And then
Okay.
committed, then snapshot isolation.
Yeah, serializable is the strongest isolation, and some actually implement via two-phase locking, or if
Yeah,
the database all also implement snapshot isolation, they go via serializable
snapshot isolation.
snapshot isolation.
Mhm.
So if you're going via two-phase locking, so you actually uh, you acquire the locks in a sequence, and you release the sequence. You hold the locks till the end of the transaction, and you release that all the logs at the end after the transaction is completed. And serializable snapshot isolation is actually uh, it is like serializable itself, but just that we keep there is no locking as such. So we actually keep track of what the transactions are reading, and so whenever the transaction is getting committed, we actually check whether there are any dependencies between all the happened transactions. So if it has read some data that was in between to the that was outputted by the transactions that were running before, but by the time it is committing, it might have already been completed. So it tries to capture the dependencies and uh, tries to implement the serializable snapshot isolation. Read write and read dependencies. Yeah. So snapshot MVCC is nothing but, so basically it gives you a guaranteed view of view at that particular time. So whenever a transaction has started, it uh, the database gives you a guarantee that it will give you all the results till that point of time. I mean, so it actually so we actually have an transaction identifier, and so all the transactions that were completed the till that point, uh, all the results of the transaction that have completed will be visible to the transaction, either that are executing or that are in progress. That won't be visible to that MVCC.
Multi-version concurrency.
Yeah, MVC. And read committed is nothing but so you the transaction mm, so you just read the data after the transaction is committed. The transaction might have multiple intermediate steps, but the transaction might not have completed, but you will read after it has been committed.
Yeah, right. Yeah.
No reads, queue, lost updates. I think I remember some of this. Uh, so lost updates, let's take we are trying let's take the snapshot ISL MVCC itself, multi-version concurrency control. So we are trying to increment a counter, and so both of the transactions try to execute increment on the same object, and they're uh, happening simultaneously. Since this is snapshot isolation, both of them see, let's say the initial value is 4. So both of them try to increment by 1, and the initial value they see it as 4 itself. So they try to increment it to by 1, and both of them update to 5 itself. But ideally, uh, two transactions are trying to update it by 1. So ideally the value should have been 6, but one of since this is a snapshot isolation, and both are having the same initial value, one of the transactions update is missing. So that is like lost update.
And here they are saying that in snapshot isolation there is no lost update.
Uh, I thought snapshot isolation only we have lost update.
Yeah, you are
No, actually see this one. Read committed, no dirty reads and no dirty writes. So that is for the read committed. In MVCC, we have reads, queues, and lost updates. In
right.
yeah.
No, in snapshot isolation we don't have read queues. So the problem with we committed was that if a long running process is seeing your data, then although individual objects have the right value, but when your long running process is reading the data in a different point of time, right? So you might see a read queue, but with snapshot isolation, you don't see the read queue, right? So this makes sense, but yeah, even more like subject, I don't remember. I think the point that if you are taking a snapshot, then uh, two transaction might see an old snapshot and they might update the value at the same time, which might be the same value. So how did you prevent no loss? I don't remember that.
Sorry, I got lost in between.
Yeah, no, I'm saying that I think this. Okay, we can probably uh, move forward, but I think this is saying that with snapshot isolation, you don't see lost update, no lost update. Because definitely there is no read queue with snapshot isolation, right?
Yeah,
The
reads queue won't be there.
won't be there. So I think they mean to say that there is no lost updates.
Yeah, there is no lost updates because of the commit moment. The transaction manager verifies if the values is obtained from snapshot isolation were still valid. If they have changed, transaction manager aborts the transaction. So you don't let it move forward. And because of that, you don't have lost updates.
And why do we see this problem in read committed? Why doesn't the transaction manager do the same in read?
In read committed, we are preventing dirt reads. So we can obtain a lock from the row and nobody else is able to modify this row, this object, until the locks release it. But in practice, MySQL, PostgreSQL don't rely on locks. They rely on a sort of a snapshot also. And for this reason, in practice, you can get lost updates if you are relying on a database that instead of implementing logs, makes use of a snapshot.
Okay. Okay. Udaya, you can continue.
Couldn't remember the other things actually. Comment.
Yeah, I remember that with snapshot isolation, then they showed this example of doctors, right? That there are two doctors who
Yeah,
value.
both are on call. Yeah. So I was actually referring to the similar example actually. But that is that is like not lost update, but I would say it is a different thing. So two doctors are on call, and we have a guarantee that at least one of them needs to be on call, and so this since there is snapshot isolation, both of the doctors try to change. Try to take leave, and they try to update the status. So they see that the count is equal to 2, and count is greater than 1, and try to change the status from on call to off. From on call, and both of them try to update the same time, and both of them, since this snapshot isolation,
and there is no since these transactions are not uh, getting tracked, that both are reading a similar data and both are trying to update the same data, both get successful in both can get successful in updating the uh, status from on call.
Mhm. Yeah.
So yeah,
Yeah.
that
Basically, it was not
is
it was a right skew, right? That they are reading some data, but they are updating something else. So, and the data which they are reading, that could have changed. So, although during the write, whatever data they're writing, they will check whether that data has been updated or not to prevent this no lost update. But still, they could see the right skew because the data they're updating is different, but the data they were reading is different, and the data that they were reading has now changed, right? The data that they were reading was that how many of them are on call, and that data has actually changed, right? So in that
yeah.
case, you could see a right skew in snapshot isolation, but if we are using serializable, then we won't see the right skews. So I think it was called phantom reads, like uh, those hidden things which have changed, but which we were using to actually write.
Phantom read, like for example, we read the range, talking in the SQL database, we read get all the record, between, let's say, 1 and 10, right? And then let's say at that time we read it, there's only 5 record come back, and then somebody write a new record to it, and then the second time we read again, now it becomes 6 record. So that's a new record insert in between. That's a phantom read.
Is that
Yeah, phantom reads you get when you have the no locks or any of the things. So even if it 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 gets those kind of reads also.
Yeah, you don't have range lock. You can
Yeah.
have lock, but you don't have range lock. Yeah. And then the other one, I think it also, I'm not sure if it mentioned, but like if we do serializable, it will hurt concurrent, right? So serializable is like, not good for concurrent, but recommit is better for concurrent because we don't lock, everything.
you will get better throughput with read committed and more better in throughput with snapshot. Sorry, less throughput with snapshot and even lesser with serializable. But then they provide you stronger guarantees. So yeah. And
Yeah,
so
depending on the applications, you pick read committed, read snapshot versus serializable.
okay, yeah. Thank you so much, Uday, for a brief overview of this chapter. Uh, so we have 10 more minutes. I think we can do one more. Let's do chapter 6. Where is chapter 6? Chapter 6. 3, 2.
It's under 7 only. Under
Should I go left or right?
go left, I think. It's wherever you were, it was right under that.
Go under 7 here. 6.
It
This is.
was
Oh, yeah.
it was some islands. Go under.
Yeah, this is 6, right?
Yeah, right there. Yeah, partitioning.
Oh, yeah. So 6th chapter was about partitioning, right? Do you want to give overview of this chapter? Partitioning. Just looking at this image and yeah, whatever you can recall.
Yeah, basically partitioning is this concept comes into play when you have data and data is scattered, or you want to partition the data based on ranges or companies or teams or geolocations, you need to partition the data. So based, so how, so you have a, so you have a requirement, and for small companies, all the data can be in one place, but once the data grows, you have to partition the data. So how do you partition it? So you partition the data um, uh, based on routing, like which routes, geolocation routing, or where you want the data, or you want to keep partitioning, like partition based on ranges, like you have 1 to 10 will go to one partition, 10 to 20 will go to other partition. There's a key kind of key based, or you can go with indexes. Based on your different indexes, you can partition the data to different areas, or you can do hash map partitioning, where based on the hash values that you get, like all the values from A to Z, based on some company and some key, you will partition the data into. So you will make sure all the data is balanced in different locations. So there are different kinds of how you want to partition the data, and that is all this thing. And so in that context, we have based on routing. So you have a data, you need to route the data based on which partitioning method you will use. So you have hash partitioning, you have key range partitioning, you have secondary indexes where you will partition it, and there's rebalancing when you think that your data is not evenly balanced, and you have some hotspots, like only some data is actively used, and you can actually rebalance it. So in terms of that is high level partitioning, but once you go into low level partitioning, you will see, like if you use hash partitioning, what are the uh, good database or applications that you can use. Like if you use hash partitioning, then Cassandra is actually good. Cassandra or MongoDB is good. Or if you use key range partitioning, then you should think of HBase and rethink DB. Or if you use secondary indexes, in that Elasticsearch or what is that other one? Elasticsearch or Solar is good. Yeah. And then basically, whenever you have documents that you want to partition, Elasticsearch is the industry standard to actually do the partitioning. So if you have some applications which are similar to like PDFs, every time you sign a document, there's a contract. So all this uh, partitioning, when you are planning to do, Elasticsearch is good. So what it will do is um, you have an index server where you'll have which will tell you like which PDF will is stored in which location, and then you have actual location of where the actual PDFs are stored. So all the data, so you will have one key location from where you can actually quickly search, and this is highly scalable, and it's very easy to search millions and billions of documents. So this is the industry standard for Elasticsearch for documents if you're partitioned. And term partitioned is, I think it is database related uh, partitioning based on date. Is that correct? Term partitioning? I forgot what is that. I don't
See, I
remember that.
mean, so these are, I mean, as far as I remember, these are secondary indexes, right? So, I
Yeah.
mean, the document might contain, I mean, some significant attributes, I mean, that we want to search on.
Okay,
So,
so that is like, okay, you have documents and document search, you have like a city or some additional attributes, age range or something.
yeah,
Okay, yeah. So that is, so you'll again repartition the documents into different key value pair so that it's easy to search the data. So high level, this is just how you want to partition the data and how you want to put the data in this for highly scalable applications. Thank you. If anyone wants to add anything, they can add, but this is on a high level, this is it.
Yeah, yeah. Thank you so much, Praveen. One thing I remember which is not mentioned here is, so these partitions are like kind of your logical partitioning of data, right? Either key range, hash range. But then there are various techniques that how these logical partitions actually map to the nodes, how you do that. So there are various things, there were various ways to do that, right? That either you assign, so either you assign some, so like one of the approach was either you assign fixed number of partitions to each node. So you say that you will assign 3 partitions to each node. So that was one way, but then the problem with that was that if your partition size is smaller or larger, by fixing this, you might not be making proper utilization of each of the nodes. So then uh, the other approach was that basically that you assign partitions on the basis of how many. The other approach was that based on your total number of nodes, you decide how many partition each of the nodes will get. So in the first one, you were fixing, but here, like you were based on your total number of nodes, you were assigning that which node will get which partition, like how many partitions will get will be assigned to each node. Because if you have large number of nodes, then you can evenly distribute those partitions among those nodes. But then the problem with this approach was in rebalancing, that if you now add nodes, then what do you do now? Like, how do you rebalance? So I think those were other things which we were, yeah.
Hotspots, right? So we want to avoid hotspots while for the data to store. So there might be some applications or companies which store lots of data, and some applications or companies which don't store a lot of data. So we should not divide all the applications in the same fashion. So depending on the application usage, once you design it, you have to change it based on the usage and have a different strategy to it to rebalance it.
Yeah. Okay. Cool. So yes, so I think we discussed 6, 7, 8, 9. We discussed 4 chapters, right? Great. Okay.
What are the strategy to rebalancing?
Oh yeah. So what were the rebalancing strategies? So I think one of the thing was mentioned was consistent hashing, that you can use. So you can use consistent hashing to rebalance, right? If you're using based partition, then you should use consistent hashing kind of thing. Otherwise, you would have to, if you rehash everything, then you would have to move a lot of data if you need to rebalance, right? And then the other thing which was mentioned, how you rebalance is depending on what approach you choose to assign these logical partitions to the nodes. So based on the approach you choose, that whether you assign fixed number of partitions to each node, or whether you decide the number of partition based on number of nodes. So based on what strategy you choose, there would be a different way to rebalance your partition. Okay, I think we are out of time now. It's time for next session. So thank you everyone. Stop the recording.
Thanks, Abhishek. Yeah, thank you.
Thanks.
Thank you.